Hello everyone, imagine you are sitting in a completely dark room, with only the faint light from the computer screen illuminating your face, and outside the window, the night wind gently howls through the tree branches, carrying the scent of damp earth after a rain shower. We are all familiar with looking up at the night sky sparkling with billions of stars, wondering where we stand in this vast universe, and whether someone out there is doing the same thing. But now, when we look down at our feet placed firmly on the ground, a vague anxiety creeps into our minds. This lush green planet, where we were born and raised, is gradually becoming suffocating with thick layers of smoke and dust covering major cities. Rivers that were once crystal clear now murky with industrial waste, and the incessant roar of vehicle engines echoing day and night. Climate change is unfolding right before our eyes, with tropical storms growing increasingly ferocious, sweeping away homes and trees, leaving behind heartbreaking cries from those who have lost everything. Environmental pollution is not just images on the news, it is the foul stench from enormous garbage dumps, dead fish floating belly up on lake surfaces, and children coughing persistently due to toxic air. Natural disasters strike relentlessly, from earthquakes that shake entire regions with the terrifying sound of the Earth's crust cracking, to prolonged droughts that cause the soil to crack like the dry hide of an elephant, and sudden disease outbreaks that spread through innocent handshakes or close breaths, filling hospitals with painful groans and the sobs of families at hospital beds. This does not stop there. Armed conflicts erupt everywhere on the planet, with the sound of gunfire thundering, bombs falling like thunderclaps, and the acrid smell of burning smoke mixed with the metallic tang of blood. Famine ravages many lands, where children with sunken eyes from starvation, bellies swollen due to malnutrition, lie curled up beside dilapidated thatched homes. Our Earth, the beautiful planet once covered in lush green forests and vast oceans, is now in serious trouble, like a living body running a high fever and exhausted. Extreme weather events occur more frequently, from floods that submerge entire cities in murky waters with the roaring sound of water sweeping everything away, to heat waves that scorch the land, causing trees to wither and animals to die dry by the roadside. Crop failures happen consecutively, with rice fields that were once golden now reduced to blackened stubble, leaving farmers standing silently by their fields with calloused hands and eyes full of despair, wondering if their families will have enough rice to eat this year. All these issues force us to pause and reflect deeply. How much longer will Earth remain a safe haven for humanity, with the population exploding and resources depleting gradually? And when will we need to search for a new home, another planet out there in the immense universe, where we can start over with hopes for a brighter future? Out there, in the dark and cold expanse of space, where light from distant stars takes millions of years to reach us, is there any world truly suitable for life, located in the relatively nearby region of our solar system? If so, it would certainly be an essential stop, a lifeline to usher in a new era for humankind, a green planet not Earth, with dense forests rustling joyfully in the wind, clear rivers flowing with gentle murmurs, and a blue sky free of any smoke haze. As of the latest updated data from observation missions such as the James Webb Space Telescope launched in 2021 and NASA's exoplanet hunting programs, we have confirmed more than 5,500 exoplanets orbiting nearby stars in our solar system. These worlds are incredibly diverse, with all kinds of sizes. There are gas giant planets many times larger than Jupiter, featuring enormous swirling storms that rage endlessly. There are small rocky planets only about the size of Earth, and some lie far away hundreds of light years, where the light reaching us is ancient from prehistoric times, while others are closer, just a few dozen light years away, allowing us to dream of sending radio signals and awaiting responses. All of them are destinations that ignite intense curiosity in scientists, who spend their lives at desks with screens full of flickering data, and foster hopes for a fascinating future world where humanity can settle and uncover new secrets. For scientists tirelessly searching for life beyond Earth, their ideal target is an Earth 2.0, a sturdy rocky planet with abundant liquid water in the form of vast oceans or rivers and lakes, and a thick protective atmosphere, like an armor shielding the planet from dangerous cosmic rays. According to astrobiology, a branch of science studying how life could exist in extraterrestrial environments, all life on Earth that we know is based on carbon as the foundation, with water serving as a crucial solvent for complex biochemical processes, such as how water helps protein molecules fold and enzymes catalyze reactions. Extraterrestrial life could also use similar components, with carbon forming long flexible chains and water as the medium for metabolism. However, we cannot completely rule out the possibility of other elements, like silicon capable of forming complex bonds at high temperatures, or different solvents such as liquid methane on frigid planets, serving as the basis for more exotic life. Besides elements and solvents, life also requires a stable energy source to sustain chemical reactions, and the most typical energy comes from stars, those enormous plasma spheres emitting light and warmth over billions of years, like our sun bathing Earth in golden morning rays. But that is not the only source. Many celestial bodies in the universe can provide energy for life, even more abundantly, powerfully, and almost eternally, and that is black holes, celestial objects representing the ultimate energy derived from tremendous gravitational forces, where space-time is bent to the point that nothing can escape. Could life exist around black holes, in environments where cosmic winds howl and light is stretched into strange red streaks? When mentioning black holes, we often immediately think of absolute destruction, a dark void swallowing everything, with nothing able to survive an encounter. The black hole would win and always win, like an undefeated predator in the universe. Black holes form when massive stars, with masses dozens of times that of the Sun, become too heavy at the end of their lives, where even core temperatures reaching billions of degrees Celsius, with seething plasma and explosive nuclear reactions, cannot withstand the terrifying power of gravity, collapsing everything into an infinitely dense point. The moment a giant star collapses is an extraordinary event, a symbolic occurrence in the universe that science can observe through propagating gravitational waves, like the echo of a gigantic atomic bomb exploding in silence. Essentially, black holes produce vast amounts of energy. They accelerate matter particles to near the speed of light, with the screeching of torn plasma, before sucking them into the event horizon, the point of no return. But can that energy source nurture life? The answer likely depends on distance, because if too close to a black hole, the radiation it emits, blinding gamma rays and X-rays, could kill any life. Imagining if a creator stood near a black hole, they might feel dizzy from the dragging gravity and scorching radiation, let alone fragile life. So how far from a black hole is a suitable position? A distance considered safe might be within the limit of 10 light-years, where the gravitational environment is stable enough for planets to orbit smoothly, similar to Earth revolving around the Sun with regular four-season cycles. On Earth, living organisms depend heavily on sunlight for survival, from plants photosynthesizing with leaves rustling in the sunshine, to animals warmed by infrared rays. If the Sun were replaced by a black hole, in principle, it would not differ much in terms of energy. According to a paper by Dr. Jeremy working at NASA, the accretion disk around a black hole, a flat structure of matter stretched into a swirling ring, could represent the Sun. It is essentially a flat band of matter moving extremely fast around the black hole at near-light speeds, emitting dazzling light and heat. All known black holes, from stellar mass ones with a few times the Sun's mass to supermassive ones at galaxy centers with billions of times, have accretion disks and are extremely bright if a planet is at a suitable distance. The black hole and its disk would be no different from a radiant star providing energy and warmth, with light flickering through the atmosphere. However, the ultraviolet and X-ray radiation from the accretion disk is also enormously high, far greater than the Sun's. This radiation has strong sterilizing power, destroying even the smallest life like bacteria or simple cells by shattering DNA with high energy. Therefore, for a planet to nurture life, it must have a thick enough atmosphere to block those deadly rays, which seems not too difficult a condition because among hundreds of exoplanets discovered via the James Webb and ground-based telescopes like the extremely large telescope under construction, many have thick clouds and atmospheres, with acid rains or strong methane winds. Additionally, we cannot rule out the possibility that many life forms could exist and thrive without direct sunlight. Typical examples are life forms around hydrothermal vents on Earth, at the dark ocean floor where boiling water gushes from crustal cracks with the rumbling of magma and a strong sulfur smell, organisms like chemosynthetic bacteria use chemical energy to live. Thus, theoretically, a life form or chemosynthetic ecosystem could exist on a planet around a black hole, as long as the planet has liquid water, with subsurface oceans under ice layers or lava lakes. Furthermore, recent studies from the European Space Agency's Ariel mission, launched in 2029, have begun analyzing atmospheres of rocky exoplanets, detecting potential biosignatures like ozone or methane imbalances that could indicate life, expanding our understanding beyond solar-type stars. Black holes, especially those in binary systems with companion stars, can provide intermittent but intense energy bursts through accretion, potentially driving evolutionary pressures similar to Earth's mass extinctions that spurred biodiversity. Next, we will consider the stability of the energy source. Our Sun is an extremely stable star, operating very smoothly and gently over billions of years, with sunspots flickering like a steady heartbeat. The question is whether a black hole is like that. The answer is certainly no, because when the accretion disk glows brightly, it might erupt with gigantic plasma flares, and sometimes it lies silent and cold like a deadly void. The time needed for a black hole to digest the accretion disk usually lasts millions to billions of years, with the tearing screech of matter gradually fading, after which it falls silent until something new, like a wayward star, is pulled in with echoing explosions. And if a black hole remains silent too long, it would spell death for life, akin to Earth enduring an ice age but not ending soon, with ice ages potentially lasting billions of years, snow covering everything white and winds cutting like knives, even longer. And if temperatures are always frigid like on Pluto with rigid methane ice, no life could exist. Clearly, for life to develop on a planet around a black hole, it would likely need to evolve to adapt to the ups and downs the black hole brings, from warm radiant phases to deadly cold ones. There would be no ease in creating miracles, as hardship and harshness forge strength, like how life on Earth has overcome numerous catastrophes. If we delve into Earth's history, we see many events occurred during the planet's formation, from gigantic asteroid impacts with terrifying explosions and dust clouds shrouding the sky for millions of years, to ice ages with glacier slowly advancing and crushing boulders. Yet life could still begin from simple sea sponges in primordial oceans, spread through tropical rainforests with birds singing loudly, and even flourish with the emergence of intelligent humans. This is so miraculous that we cannot explain how life was created from inanimate chemical mixtures, so there is no reason life could not begin and develop on planets around black holes, on any planets we observe outside the solar system. How many of them are suitable for life or habitable for humans? The answer: we are not entirely sure, but in reality, there are so many that current technology cannot fully count, and according to new data from the European Space Agency's Plato mission scheduled for launch in 2026, we could detect thousands more planets in the habitable zone. For us humans, we need a truly safe planet with all accompanying conditions like oxygen to breathe, drinkable water, and moderate temperatures. This is not because our requirements are high but because our adaptability and endurance are very poor compared to extremophiles. For many other life forms, a deadly planet with poisonous winds or atmospheres thick with toxins might not be an issue. They could evolve with hard shells or unusual metabolisms. Hopefully, in the not-too-distant future, with next-generation telescopes like NASA's Habitable Worlds Observatory, we will find such life on a planet not far from Earth. I am certain that discovery will completely change how we think about the universe, about life, and even about a creator, opening an era of interstellar exploration. Hello everyone, this is our home, a remarkably humble planet with vast oceans where waves lap gently and majestic mountains shrouded in white clouds. Our star is the same, the Sun, nothing particularly standout compared to billions of others, just a warm golden sphere illuminating a small planetary system. More than 100 years have passed since the moment Edwin Hubble, sitting by the telescope with eyes weary after a long night of observation, discovered the universe is expanding, with galaxies moving away from each other like balloons released in the wind. This truly has profound meaning, letting humanity know our smallness compared to the immense universe. When extending our view beyond the solar system, we are moving within a gigantic stellar swirl called the Milky Way, with the supermassive black hole Sagittarius A star at the center emitting faint radio waves. It is similar to thousands of billions of other swirls existing in space, each with hundreds of billions of twinkling stars. Why is the universe so vast? Why are there so many galaxies, with perfect spiral shapes or faint elliptical ones? Is that all there is? One fact is that as technology advances, from the Hubble telescope to James Webb with its 6.5-meter primary mirror collecting infrared light, the number of galaxies we catalog in the universe increases, like peeling endless layers of the cosmic onion. About 40 years ago, before the Hubble Space Telescope was born, many cosmologists thought the number of stars in the Milky Way could reach hundreds of billions, and the number of galaxies in the universe might be similarly numerous. Of course, those statistics were just personal opinions at the time, everyone thinking it was exaggerated to emphasize the universe's vastness, with long nights observing beside silver photographic plates. So in reality, how many galaxies exist, and how do people calculate that? Through long nights analyzing data with the humming of computers. First, we must mention the number 170 billion. It originates from detailed observations by the Hubble Space Telescope, called the Hubble Extreme Deep Field, a project lasting with the telescope's motor slowly turning toward a dark patch of sky. To create one such simple image, Hubble had to work continuously for 10 years, starting from 2003, by collecting faint light from very deep space. Those dim rays only 1/10 the brightness the human eye can detect in a quiet dark night. The work continued until the end of 2012 to complete. It is a compilation of many small images stitched together, aimed at a small region of sky in the constellation Fornax, the photo containing about 5,500 small galaxies, occupying 1/32 millionth of the sky area we see from Earth. Thus, simply multiplying by the expansion factor, we get the number of galaxies fluctuating around 170 to 200 billion, and when excluding errors from light noise and cosmic dust, one can state that in the observable universe there are at least 170 billion galaxies existing, each with its own formation history from the Big Bang. This is clearly a staggering number, but it is not even 1/10 of what we now consider correct according to new models. As of 2016, a study from the University of Nottingham discovered that in a given volume of space, the number of early galaxies could be 10 times the number we actually observe, most of those galaxies relatively small and faint, with masses equivalent to dwarf galaxies with a few billion stars. This leads to the conclusion that 90% of galaxies in the observable universe are too faint to be seen with modern telescopes, that number equivalent to about 2 trillion galaxies. Thus, in just 3 to 4 years from 2012, the number of galaxies in the observable universe increased tenfold thanks to deeper infrared data analysis. Is that the final number? It seems not. With the latest estimates from James Webb in 2025, the number of galaxies in the universe could range from 6,000 to 20,000 trillion, thanks to discoveries of distant redshifted galaxies from the early universe. Recent observations from the Nancy Grace Roman Space Telescope, launched in 2027, have further refined these counts by imaging ultra-deep fields, revealing even fainter primordial galaxies and pushing estimates toward the higher end. One thing to affirm is that the number of galaxies we see in the observable universe today or in the future will always be a finite approximation, because space is always expanding at an accelerating rate due to dark energy, light becoming increasingly faint as it travels through cosmic distances. We must accept that some places are forever beyond reach, like distant islands in an endless ocean. Moreover, the speed of light is a finite number, about 300,000 kilometers per second, while the expansion speed of space is even faster than light on large scales. This means even if you built a spaceship flying at 99.99% the speed of light, with ion engines roaring, and started traveling right now, still 97% of galaxies in the universe you could never reach, because the observable universe's boundary recedes faster. Why is that? Let's do a simple calculation to visualize. 1 light year converted to distance is about 9,500 trillion kilometers. The current Hubble constant is 68 kilometers per second per 360,000 light years. Converted to years, it is approximately 2,144 trillion kilometers per 360,000 light years. Now to know how much the universe expands in 1 year, take the 93 billion light-year diameter of the observable universe divided by 3.2 million years, then multiplied by 2,144 trillion kilometers. The result is 6.1 times 10 to the 13th, equivalent to 61,000 trillion kilometers. That is a crazy number. Even traveling at light speed for 1 year, you can only move 9,500 trillion kilometers. Yet in the same time the universe has expanded by 61,000 trillion kilometers, like distances between galaxies stretching with invisible tearing of space. Perhaps from now on we should not wonder why light travels so fast, but why in such a vast universe light travels so slowly compared to expansion. Returning to the number of galaxies in the universe, the remoteness of space limits our view. The farther galaxies are, the fainter their light, like weak glows in fog, leading to the consequence that to observe even farther galaxies their light must be brighter than nearby ones, meaning newly formed small galaxies with faint light cannot be seen. Regarding telescopes, they are designed to observe the past where only primordial galaxies existed, very small and faint with primordial hydrogen gas. Thus, the number of galaxies we actually observe in the observable universe will always be finite. Along with that, some places in the universe will forever be unfamiliar regions never explored, like secrets buried in eternal darkness. Here some might wonder if we just build larger and more powerful telescopes everything would be solved. In theory yes, but we have practical limits. You cannot build a telescope infinitely large with diameter at least the solar system. You cannot observe the entire sky at once with high resolution, and the telescope cannot operate forever without breakdowns. If humans could make such a machine, I am sure producing a near-light-speed spaceship would not be harder than making a car today, but clearly there are limits humans cannot overcome. We can only upgrade technology gradually and push boundaries a little farther step by step, like the James Webb Telescope, a modern and powerful machine with a gigantic sunshield, but everyone knows it cannot reveal everything about the universe. About 20 years ago, when our observation technology was relatively developed with Hubble, we could only confirm 50 to 60 galaxies in the local group with an estimated diameter of 4 to 5 million light-years. To the present, the number of galaxies in our local group has reached 110, most small relatively faint ones, even smaller than the Magellanic Clouds with weakly twinkling stars. Essentially, most of these galaxies are called satellite galaxies to those with mass and diameter equivalent to our Milky Way. In the most observable region, the number of satellite galaxies per such galaxy fluctuates around 30. This number decreases as distance increases, and if distance reaches a few hundred million light-years, the number of satellite galaxies drops to 0.6 per galaxy. In our local group, the Milky Way and Andromeda are the largest and possess many satellites orbiting like loyal children. In fact, if fully observed and counted, a galaxy equivalent to the Milky Way would have from a few dozen to hundreds of satellites. Extrapolating to the entire observable universe, the total number of galaxies plus their satellites could range from 6,000 to 20,000 trillion. This is a very large number, but it does not affect much the number of stars we previously catalogued, because satellite galaxies are relatively small with only tens of thousands of stars compared to hundreds of billions in large galaxies, amounting to about 0.01%. Thus, the 2 trillion galaxies in the observable universe we have long counted are just the tip of the iceberg. There are many more galaxies telescopes cannot see because they are faint or too far. And if on each such galaxy a civilization emerges, or simply a planet with life featuring cities of light or rustling forests, then this universe is truly a vibrant one, a universe of endless diverse life. Hello everyone, we all know modern physics theory that scientists have painstakingly built so far is not complete, with lively meetings in laboratories full of formula boards, yet all efforts to find a deeper theory lead to disappointment. Everything we know is encapsulated in the Standard Model, a theoretical framework describing fundamental particles and interaction forces. It shows the universe is created comprising matter and antimatter. When these two types collide, they annihilate each other to produce pure energy. For example, when an electron collides with a positron, usually this combination produces a pair of gamma photons with blinding light. In some higher energy cases, it can create particles like Z bosons, W bosons, or muons with swirling orbits. According to symmetry theory, after the universe's birth with the Big Bang exploding energy, matter and antimatter should annihilate completely, leaving an empty, meaningless universe. But somehow ordinary matter remained to form spiral galaxies, blazing stars, green planets, and complex life to this day. This anomalous existence is still one of physics' greatest mysteries, keeping scientists tossing and turning beside late-night coffee cups. Scientists have proposed many hypotheses to explain that asymmetry, but in truth we do not know which is right or wrong. One of the most reasonable hypotheses is that after being born, matter decayed to create even more matter, gradually breaking the balance, resulting in the universe we observe today almost 100% ordinary matter. Although particle decay may not be the entire cause, it shows supersymmetry theory is imperfect and scientists need to reconsider. Thus there is a major problem to solve. Was the universe symmetric after birth or not? If symmetric, every particle we know in the Standard Model would have its own partner. Besides, there are still dozens of other supersymmetry theories describing everything in nature in reverse. Asymmetry or incomplete symmetry could hide many new particle types and new physical phenomena. Because all particles in the current Standard Model have antiparticles, if ordinary matter decays to more particles than antimatter, certainly in nature there are still particle types we do not know. Before delving into deeper issues, we need to know why the scientific community believes the universe was born comprising matter and antimatter, why people know that while today's universe is all ordinary matter. Of course, this is not baseless prediction. When particle and antiparticle combine, they create high-energy photons, and clues about what happened are clearly shown through cosmic microwave background radiation, the oldest photon layer of the universe we record today via telescopes like Planck with cold data from space. Accordingly, the ratio of ordinary matter particles to microwave background radiation is 1 to 10 billion, meaning for every ordinary matter particle existing in the universe, there correspond 10 billion microwave photons. This ratio shows at the universe's birth moment the number of matter and antimatter differed extremely slightly. For every 10 billion antiparticles born, there were 10 billion plus 1 ordinary particles also born. After colliding to create energy, the remaining ordinary particles continued linking to form what we see today. Essentially, this is an extremely small asymmetry, but because the number of particles was so large, the consequence is not small. Today we live in an energy-filled universe, ordinary matter component occupying about 5% of the universe's total mass energy, and scientists are still trying to understand why the universe has such a symmetry. Though only a very small asymmetry, it is an extremely large mystery. So how do scientists decode this problem, and have they decoded it so far, with experiments at the Large Hadron Collider and other accelerators? Overall, this is certainly a difficult problem because it is not for nothing called one of physics' greatest mysteries. In recent decades, scientists have tried to find what is called the electric dipole moment of the electron, one of the most difficult and time-consuming searches in science history, with cold laboratories and vacuum pump humming. So what is the electric dipole moment of the electron, and what does it mean? Essentially, the electron is a very small charged particle, however it does not exist simply. Surrounding the electron is a cloud of virtual particles similar to how electrons surround atomic nuclei. These virtual particles act around the electron like magnetic fields of bar magnets with invisible pull-push forces. In quantum mechanics, this is called the electron quantum field. Every particle has such a field and they influence each other. If there are many strange particles corresponding to unknown fields, they will affect the electron cloud, making it asymmetric. In other words, that interaction causes electric dipole moment. The electron's electric dipole moment is manifested by the difference between mass center and charge center. This difference has never been detected and likely much smaller than what experiments can measure with high precision. If this is true, scientists will have to add new particle types to the Standard Model to explain the matter-antimatter imbalance. Now, linking to supersymmetry theory, if nothing happens, the electron exists as a perfect sphere. Conversely, the electron would be slightly elongated. An electron, not a sphere, means its electric dipole moment differs from zero. The scientist's task is to check if electrons are round or elongated. The essence is measuring the difference between mass center and charge center. Everything sounds not too complicated, but when deeply into the experiment you see how difficult it is. The electron's size is already very small, so small no specific number confirms it. Some old calculations said electrons smaller about 1,000 times a proton, but today we know even smaller with experimental limits, yet people must measure its mass center difference. To detail this experiment would take much time, so I will summarize briefly for easy understanding. For an electron experiment, people place the atoms to study in a vacuum chamber so they contact no other atoms. The chosen atoms in this experiment are ytterbium monofluoride. In the experiment, when atoms are charged, they are easily pulled by magnetic fields flying from one end of the chamber to the other, with the laboratory designed as a long tube about 1 meter in the middle where atoms are observed. Normally that section is about 1 meter long. The weakness of this method is atoms move very fast, up to a few hundred meters per second, so actual observation time only lasts about 1 millisecond, causing much data to pass uselessly without recording. To overcome the drawback, scientists reverse magnetic poles fast enough at both chamber ends. Atoms now, instead of flying one way, are pulled back and forth in the middle, and this method is called magnetic trap. If turning the laboratory chamber into a circular shape, atoms inside will move in circles. This innovation increases observation time from 1 millisecond to 3 seconds, and that is a breakthrough change. Measurement time only interrupted by molecules tending to decay to more stable lower energy forms. The experiment's purpose is to measure the smallest magnetic field oscillations with the highest possible precision. Data collection like this lasts about 2 months with over 100 million electrons recorded. Then scientists use more than 2 years to calculate errors through years of work. The final result of the experiments is zero. No electric dipole moment of the electron recorded, at least this time. Fearing unwanted errors affecting results, scientists are planning a more elaborate modern experiment lasting about 10 years with cryotechnology and more precise lasers. However, whatever said, to date the electron's electric dipole moment is still zero, and this is a result saying much. The electrons themselves are still perfectly round spheres, supersymmetry theory not yet overturned, and the antimatter mystery remains. If you have any antimatter particle and throw it into the Milky Way, that antimatter particle will exist at most about 300 years before combining with a similar matter particle and self-destructing with a small gamma explosion. That shows the amount of antimatter compared to ordinary matter in our galaxy is 1 in 10 to the 15th. Additionally, farther observations from a few hundred million to 3 billion light-years also show existing antimatter in the universe almost none, because if there were, it would interact with ordinary matter and create observable gamma or X-rays from Earth with telescopes like FEMI. Today scientists can be certain the observable universe we see is composed of 99.999% ordinary matter, and the cause of this asymmetry to date remains a grand mystery. Ongoing experiments at the Future Circular Collider, proposed for the 2040s, aim to probe even higher energies for clues to charge parity violation extensions. Hello everyone. The ultimate fate of stars is often extremely energetic events with blinding light and propagating shock waves, and the level of those events is closely related to its mass. But why often? Not always, because sometimes stars influence each other. A normal star can completely trigger another star's supernova explosion when close enough, with gravity pulling each other, meaning even without sufficient mass the star can still end its life with a spectacular explosion if receiving external help. Even when the star is dead, it can explode once more with echoing blasts through space. Basically, that is called evolution. Each normal star can only go through the main sequence cycle once with stable hydrogen-helium burning, but it can evolve multiple times to become stronger versions, and one of the most common evolved versions is the white dwarf. According to statistics, up to 97% of existing stars in the Milky Way will evolve into white dwarfs when their main sequence cycle ends, with outer shells blown away into beautiful nebulae. Regarding the main sequence cycle, as I have said much in previous videos with core temperatures millions of degrees, this video we will focus only on white dwarfs. So what is a white dwarf? A white dwarf is essentially the very dense and hot remaining core of a dead star. This core is so dense its diameter is only slightly larger than Earth, but mass can be half the Sun's. According to some NASA documents, the average density of white dwarfs is 1 million tons per cubic meter. Denser than Earth nearly 200,000 times, and denser than the Sun over 700,000 times. Accompanying that is surface gravity, terrifyingly about 350,000 times Earth. If you weigh 70 kilograms on Earth, then standing on a white dwarf you would weigh 24,000 tons, while on the Sun you would weigh nearly 2 tons. Many might hear this and think something wrong with the density ratio, but no, it is not wrong. Earth's average density is 5.5 tons per cubic meter, while the Sun, though very heavy and gigantic, has average density only 1.4 tons per cubic meter, lower than Earth nearly 4 times. The Sun's structure, mostly hydrogen and helium plasma, deeper in the very high core temperature, releases enormous radiation pressure outward. This radiation pressure prevents matter from falling due to gravity, leading to, though total mass enormous, but average density only equivalent to Jupiter with thick gas layers. Returning to white dwarfs, besides possessing dense density, white dwarfs also have very high temperature, at least about 100,000 Kelvin according to spectral analyses from observing white dwarfs with faint brightness. The surface often covered by a thin atmosphere ranging from 10 meters to a few tens of meters. The atmosphere's composition mainly hydrogen and helium, especially some few atmospheres covered by carbon, oxygen, and heavy metal components. So what do these informations say? First, there is a paradox that white dwarf temperature hot to hundreds of thousands Kelvin, but it only has faint brightness compared to the Sun. The Sun's surface temperature only about 5,500 degrees, but its brightness very dazzling. Our Sun is recorded brighter than 85% of other stars in the Milky Way, yet its surface temperature very modest. Why like that? Actually, this is not too complicated. We can see similar throughout the universe, where brightness often proportional to surface area. For example, the star Betelgeuse, one of the brightest in the Milky Way, its surface temperature about 3,000 degrees, but brightness 250,000 times our Sun. The reason from its enormous surface area, this star diameter larger than Sun at least 1,400 times, surface area larger or equal to 1.22 times 10 to the 19th square kilometers. Our Sun's surface area 6.08 times 10 to the 12th square kilometers. Thus in area the Sun loses by more than 2 million times, so brightness also considerably less. Similar to one 500-watt bulb from far looking darker than 5,001-watt bulbs combined. For white dwarfs the same, though possessing very high temperature value, but because size too small, brightness also very modest. This also leads to, though around the solar system many white dwarfs, but we cannot see any star with naked eyes. The closest white dwarf to Earth is Sirius B. Everyone knows Sirius, the brightest night sky star, but Sirius actually a binary system with one type a main sequence star and the other a faint white dwarf. If we could fully catalogue white dwarfs, perhaps also extremely abundant celestial type in the universe, it is the product born when a small to medium star ends its life cycle. Most stars existing in the universe today belong to second or third generation since universe formation. Those stars ranked in low metal population, often small mass, so in distant future white dwarfs could be the most abundant celestial type in the universe. This also means opportunities for life increase, though sounds unrelated, but white dwarfs evaluated as the source producing most carbon element in the universe. Recent simulations from the Gaia mission's data release in 2023 have mapped millions of white dwarfs in the Milky Way, confirming their role in enriching interstellar medium with heavy elements. To understand more about this issue, we come to white dwarf structure. According to scientists, white dwarfs structured mainly from carbon and oxygen, and to synthesize carbon and oxygen the star must go through the process called triple alpha. Specifically in the phase the star puffs up its temperature hot enough to burn helium-4. When two helium-4 fuse create beryllium-8, but beryllium-8 very unstable, it immediately decays into smaller particles only in 8.19 times 10 to the minus 17 seconds. However, in that short moment, if beryllium-8 not yet decayed, it can combine with another helium-4 to reach resonance state. This similar to 3 helium-4 combining. Next, the resonance state immediately decays into 3 helium-4 as initial, but every 2421 such decays there is one time carbon-12 created, meaning probability to create carbon-12 is 1 in 2421. This ratio increases considerably if star temperature reaches 1 billion Kelvin. After carbon-12 created in large numbers, it can continue combining with another helium-4 to create oxygen. To this phase, if star temperature and pressure still increase, neon and magnesium start synthesizing. However, if star mass not exceed 8 times Sun mass, it cannot create much neon and magnesium. Usually such stars end at carbon and oxygen. In summary, we see carbon and oxygen are products created when the star starts synthesizing helium-4 through triple alpha process. In some cases, when star mass falls about 8 to 10 times Sun, it can create non-carbon white dwarf with main components oxygen, neon, and magnesium. Regarding white dwarfs, after formation their core temperature can range from 5 to 20 million Kelvin, yet no nuclear fusion process occurs. The star itself gradually cools slowly, with predictions the cooling process can last a few 100 billion years. The reason for slowness due to star density too large plus the outer shell of white dwarf capable of blocking radiation, making photons difficult to escape. White dwarfs, known as a stable celestial type, it can maintain gravity pressure thanks to electron degeneracy pressure as mentioned in previous videos. Electrons are particles following Pauli exclusion principle, meaning inside an atom electrons can only occupy one unique quantum state matching its energy level. Inside white dwarf matter compressed extremely tight, this compression makes electrons no space to change energy levels, and Pauli principle not allow it to seize another electron's energy state nor yield its energy state to any electron. At this time electrons fall into situation though carrying very large momentum but cannot move. That compression creates enormous pressure, keeping white dwarf from collapsing by gravity. If pressure maintained continuously, electrons gradually stripped from parent atoms. At this time nuclei losing electrons become a collection of positive ions floating mixed in a sea of electrons. This called plasma state of solid, though very dense and solid, but they act like gas. Scientists call this electron degenerate matter state. When matter reaches this state, it acts different from ordinary matter. With ordinary matter, when increasing mass, its volume also increases like a heavy person, always looking bulkier than a light one, but with white dwarfs different. When mass added, its volume smaller because gravity increases pressure on electron degenerate matter, making particles pressed closer. When the white dwarf becomes considerably smaller than Earth size, that is when electron degeneracy pressure nears its limit, it can explode anytime. According to scientists, a white dwarf will explode when its mass exceeds 1.4 times Sun mass. The explosion will release large amounts of unburned carbon and oxygen into space with light brighter than the entire galaxy. And as known, the basic element creating life is carbon, ourselves as any other life form on this planet, all created from carbon molecular structures. And if white dwarfs truly the key origin of life, then we can somewhat predict the explosion period of life in the universe has not really happened, it is just beginning, with billions of white dwarfs waiting in the aging universe.